Start the third talk by Frederico Bianchini, who's going to talk about on the Ramanujan vector field modulo P.
Okay, thank you all for coming. Thank you, Hossein, for inviting me to talk here today. As the title suggests, I'm going to talk about the Ramanujan vector field modulo P. The present work was carried out with the support of CNPq, which is the funding agency here in Brazil, and also partly developed in the IHES, because I was there last year for a month. So the talk is divided in 3 parts. Okay, so at first I'm going to give some motivation for you, then some preliminaries, like some technical stuff, and at last I'm going to compute the pth power of the Ramanujan vector field, which is the main result. This talk is more like computational. I'm not going to go too much into conjectures and things like that Hossein and Florian and Lucas also are talking about today. And the motivation is the following. It started last year with Hossein was trying to find a method to prove integrality of mirror map and in his context they are called Calabi-Yau differential modular forms, which are not given by hypergeometric functions. And in the hypergeometric case, the integrality is proven using Dwork's method, which is from like a p-adic analysis setting, right? So he started to look at this kinds of vector fields. So there's modular vector fields, modulo P, and their pth powers. And he developed a method to show P integrality of the Eisenstein series E2, E4, and E6, which we already know they are integral. They have integral coefficients, right? Using properties of the Ramanujan vector field modulo P. Okay. So this is what started. We started looking in. This is why we started looking to this vector fields modulo P. Okay. So this is Hossein's paper, and here in the abstract he tells exactly what I just talked to you. Okay. And the present work is still preliminary. I still have some things I want to do, like try to generalize this thing to other vector fields and see what we can get. It is a spin-off of Movazati's work, and what we do is we compute the pth power explicitly, okay? So the preliminaries are as follows. It's going to be basically algebraic geometry and algebra setting. Okay, so we're going to see some differential equations, but we're also going to see some algebraic geometry going on, but just in this beginning. So we consider 3 independent variables. Okay, so we define this delta, which is the discriminant of this cubic polynomial here. Okay, we consider this fractal R is this graded. This is a graded algebra over Z 1/6. So we can divide by primes 2 and 3. Okay, in our case. And here, to our purposes, we consider special weighting on the variables. Okay, so T1 has weight 2, T2 has weight 4, and T3 has weight 6. Okay. We denote as capital T the spectrum of this ring. Okay. It is an open affine subscheme of the affine space in 3 dimensions over Z 1 over 6. And moreover, we consider the elliptic curve given in affine coordinates by this. It's a modified version of the Weierstrass equation where we just translate the variable x, okay? And that's why we have to invert delta here so that we obtain like a family of elliptic curves, okay? So that we get all the geometric fibers are genus 1 smooth curves, okay? The Ramanujan vector field is a derivation in the global regular functions of T, or in R, in Gothic R, okay, and is given by this this equation, okay. As Hossein said, this can be translated to a differential equation setting, and it has Ramanujan's name because it comes from the Ramanujan system of differential equations satisfied by E2, E4, and E6, okay? But you will see that the coefficients are a little bit different, and that is because we do a little bit of a change of variables, but it's the same as the differential system defined by Ramanujan, okay? Which is this one, yeah. I forgot I put this slide. So this is Ramanujan system, and you will see that this vector field is a little bit different, but it's just a change of variables, okay? What is special about this Ramanujan vector field is that when you consider the Gauss-Manning connection of the family, okay, so here we take global sections on everything. So the Gauss-Manning connection usually is on the sheaf of the first cohomology bundle, okay, but we are taking global sections everywhere, so we get an integrable R connection in the R module given by the first de Rham cohomology of E over T, okay, the relative de Rham cohomology of E over T. So Hossein computes this connection explicitly, and for this basis here, which is the differential forms of first and second kinds, okay, in the elliptic curve. And he shows that when you compose with the Ramanujan vector field, it's a very simple thing. So dx goes to x dx over y, and x dx over y goes to 0. Okay. This turns out to be a very special property, and this is generalized to families of Calabi-Yau manifolds by Movazati, by Yunus, who is here, by Felipe, who also is in the audience, I think, and to higher dimensional abelian varieties by Tiago Fonseca, and that's all that I know, I think. Maybe there are more people working on these things. And the fruitful applications of this, well, solutions to these vector fields, they give generators to algebras of quasi-modular forms, okay? And as in the case of the Ramanujan system, right? We studied the original case for elliptic curves in characteristic P greater than 5, greater or equal than 5, so we are not considering the case 2 and 3. So for this purpose, we have to go through some congruences that exist between Eisenstein series, okay? So for each positive integer k, the kth Eisenstein series has this Q expansion, okay? I'm not going to go too much into detail. They are modular forms for k greater than 4, and E2 is quasi-modular, okay? E2, E4, and E6 are algebraically independent. They generate the C algebra of quasi-modular forms over C, okay? But Serre and Swinnerton-Dyer, they show, this is from the 70s, that for each prime greater or equal to 5, this series, they have coefficients in z, p, where zp here is the localization of z in the prime ideal p. So we are taking rational numbers and excluding, like in the denominator, there can be any p, okay? And they showed that modulo p, EP minus 1 is congruent to 1, and EP plus 1 is congruent to E2, okay? Since E4 and E6 generate the algebra of modular forms, we can consider polynomials AP and BP such that this happens, right? So AP of E4 and E6 is EP minus 1, and BP of E4 and E6 is EP plus 1, right? It's not difficult to show that they both have also coefficients in Z localized in P. And so we can consider the reduction modulo P, okay? And in our setting, since we are making a slight change of coordinates, we are considering this alpha and beta that I call alpha P and beta P here, which is just, well, this change of coordinates here. So alpha P of T2 and T3 is AP of 12 T2 minus 216, etc. And alpha P and beta P, for me already, I'm considering them modulo P. So I'm tensoring by FP here, okay? These quantities, alpha P and beta P, in our case, they are very, concrete. But they can be defined more generally for any pair elliptic curve over a characteristic P ring and holomorphic differential. And they define modular forms in the sense of cuts, okay, of weights P minus 1 and P plus 1, respectively. They appear, okay, so these two polynomials, they appear everywhere when you're dealing with modular forms modulo P, okay, or elliptic curves modulo P. To cite a few, this is Swinnerton-Dyer's paper where he proves the congruence I just showed you. And these are papers by Katz. And Katz recently studied the invariant beta P in a paper very recently in 2021, okay? So now we proceed to the last part where we compute the P's power, okay? So for each prime P, we take everything modulo P. We take our setting modulo P, okay? So R sub P is going to be this polynomial ring here, which is just Fp of T1, T2, T3, and we invert delta. Tp is just taking the spectrum of this ring. We reduce the elliptic curve modulo P, and we still denote E, the Ramanujan vector field modulo P, okay? So the theorem, the computation that I did was this one, okay? So for every prime greater or equal than 5, the pth power of the Ramanujan vector field in this RP basis that I'm going to define in a bit for you. Okay, so this is a basis of this algebra of derivations. Is written in this way. So the first coefficient is alpha p squared. The second one is 1 over 12 beta p plus T1 alpha p squared, etc. So there are quadratic polynomials in alpha p and beta p. Okay? And this was something that we saw, like when we were making computations, we stumbled across a number of relations that led to something like this, and I made like a number of experiments in the computer to arrive in the right conjecture, and then we proved it. Okay, so this there was a computational part to this work here. The first observation that I'm going to make is this one. For primes p equal greater than 5, I mean, this works in characteristic 0 as well, but I'm stating here modulo p, okay? So this derivation, this Lie algebra, is a free RP module of rank 3, and the following derivations, they define an RP basis for it, okay? So what I'm saying here is that, let me continue. E is the Ramanujan vector field. F is just the derivation with respect to T1, okay? And H is like an Euler vector field here, okay? So because T1 has weight 2, T2 has weight 4, and T3 has weight 6, this is like an Euler vector field, okay? And they satisfy the SL2 relations. So I'm not saying that this Lie algebra is isomorphic to SL2 because it is over FP, it is infinite dimensional. I'm just saying that there is an RP basis for it, which satisfies the SL2 relations, okay? And this was known to Hossein and to Yunus as well for a long time. This is not my work. For any characteristic P ring, so as Hossein already talked about, we can take, for any derivation, we can compose it with itself P times, and we still get a derivation because Leibniz rule is still valid because of binomial theorem, things like that. It's very simple to prove it. And well, the first step to compute e to the p is writing e to the p in this basis. Okay, so we know that there are 3 coefficients, R1, R2, R3, such that e to the p is written like this. Okay. Using the SL2 structure, here I'm commuting e to the p with e, and this must be 0 because, I mean, e to the p commutes with e, right? We arrive in this differential system satisfied by R1, R2, and R3. Okay? And this will be the first part of the proof after. And now we start using stronger results that were given by Sunerton Dyer in his paper from the 70s, which the paper basically is, is a bigger picture actually. He's doing some kind of modularity for modular forms to prove congruences between the tau coefficients of the discriminant function. Okay, but in the end, in one part of the paper, he develops this small theory about modular forms modulo p. Okay, and he proves a series of results, and in one of them is about derivating the beta p and alpha p polynomials, and the translation of their theorem to this setting is the following. Okay, so this polynomial here, 1/12 beta p plus t1 alpha p, is the first integral to the Ramanujan vector field. Okay. The ingredients of the proof are basically, well, you use the Q expansion of the series, the Serre derivative, and the congruences that we already stated. Okay. So a corollary to this is not difficult to show, that if you take those 3 polynomials that I'm stating, they are the coefficients for the 5th power, okay? They satisfy the differential system. Okay, so the differential system that I stated here. Okay, so the differential system. It is satisfied by the three polynomials that I want to show that are the coefficients of the pth power. Okay. Here, Q expansion. Just to continue, I have to talk about this Q expansion. I'm calling. You may call a solution to the vector field, but I'm calling Q expansion because I'm taking a polynomial and giving it a Q series to it. Okay. It is this ring morphism which takes polynomials, okay, and gives a series with coefficients in FP. Since I'm here, I have delta as an inverse, okay, as an invertible element. I have to take rational. They are rational functions here, so I have to take Laurent series in the codomain, okay? And this is simply given by this. This map is simply given by this, okay? So T1 goes to E2 minus E2 over 12, T2 goes to E4 over 12, and T3 goes to minus E6 over 216. And basically, these three series are the solutions to the Ramanujan vector field, okay? Okay, so why do we care about this Q expansion? For two reasons. The first one is that we can find polynomial relation between quasi-modular forms modulo P, and they define a solution, as I just said. Okay, and what do I mean about solution? I mean that this diagram here commutes. Okay, it's just when you take a polynomial, you apply the Ramanujan vector field, and then you do the Q expansion. It's the same thing as doing the Q expansion and derivating with respect to theta. And theta here is the same theta that Florian talked about. Okay. So another result of Stirton-Dyer translated to our setting is the following one. So for each prime greater or equal than 5, the Q expansion morphism has this kernel here. Okay, has this kernel here, and this can be rephrased in the following sense. The only non-trivial polynomial relations between quasi-modular forms modulo P are the two that we already know that were given by Stirton-Dyer. Okay. So now we have all the tools to compute the pth power. Okay. So we recall the statement. For each prime P, the pth power of the Ramanujan vector field in this RP basis is written as this thing. Okay, so we have quadratic polynomials in alpha P and beta P, and this guy here we already know it's a first integral. So the proof is divided in 3 steps. The first one, we show that it is sufficient to prove the equality R1 equal to alpha P squared. The second one is we show that alpha P squared is the only polynomial of degree 2P minus 2 having Q expansion 1. And the third one is showing that R1 is independent of T1. It has degree 2P minus 2 and Q expansion equal to 1. Okay? The first part comes from the differential system. Okay, so using the EP commutes with E, we got we get that differential equation. We know that alpha P plus beta P plus T1 alpha P satisfies it. Okay, and yeah.
I'm sorry. By Q expansion equal to 1, you are meaning that if we do Q expansion, then the constant term is equal to 1, right? This is the.
No, it's exactly 1.
So the constant term is 1 and the other coefficients
are 0. Yeah, modulo P. Okay, so
Equal to 1 modulo P.
I'm saying that alpha P of E4 over 12 E6 over 216 is 1 here in this ring.
All right.
Okay?
Right. Equal, congruent, yes.
Okay? Next, we want to show that alpha p squared is the only homogeneous polynomial of degree 2p minus 2 with Q expansion 1. Okay? So we consider the Q expansion morphism restricted to polynomials of T2 and T3. Its kernel is alpha p minus 1, and actually this is Swinnerton-Dyer's original theorem. Okay? Now we take some f, which is homogeneous of degree 2p minus 2, such that it has Q expansion 1. Then f minus 1 is in this kernel. So there's some divisor here, okay, some d. And then we analyze all the possible degrees, all the homogeneous parts in each of these polynomials. And we conclude that f must be alpha p squared. Okay? It's not difficult. And for the last part, we have to show these three things. So the first item, that R1 is homogeneous of degree 2p minus 2, is a simple thing. So E is written as this. E1 dt1 plus E2 dt2 plus E3 dt3. And, well, T1 is homogeneous of degree 2, and E1 is homogeneous of degree 4. So this guy is homogeneous of degree 2, and this one is homogeneous of degree 4, and this one is homogeneous of degree 6. So this is homogeneous of degree 2, and the same thing for this last one. So what happens is that when you take e to the power p, you get a homogeneous vector field of degree 2p, right? So you write, it's just a matter of writing the thing like this and analyzing each degree. Okay, so this coefficient needs to have 2p minus 2 degree, homogeneous of 2p minus 2 degree, because this one has degree 2. Okay. The fact that R1 is independent of T1, we have to consider the bracket e to the p with f. And this gives 0. It's not difficult to show that. You just have to use the SL2 relations. And this implies that f of R1 is 0. But f is the derivative with respect to T1. Okay? So it doesn't depend on T1. Okay? And the fact that R1 has Q expansion 1, we have to use another fact. The fact that when taking theta to the p in f in this ring here, when you take theta to the p, it is equal to theta. Okay, and this is just because of Fermat's little theorem. Okay. So using this, we can show, and using that the Q expansion is like a solution to the vector field, we can show that EP minus E actually sends everyone. So EP minus E of anything is in the kernel of the Q expansion morphism. Okay? And with this, one can show that all the coefficients of EP minus E, when you write it in this basis, they are also in the kernel, okay? But the first coefficient is R1 minus 1, so R1 has Q expansion 1, okay? And this finishes the proof. Here are some of the references. Oh, so this is Surrenton Dyer's original article that I use a lot. And these are Katz's articles where these polynomials alpha p and beta p appear. Okay. This is Hosseini's original article where he studies the Ramanujan vector field. And this is the last where the beta p is studied by Katz. And this is where Hossein studies the Ramanujan vector field modulo p as well. Okay, so that's it. Thank you.
Any question?
Okay, so what are like the next steps? So why is it good that you now have a way to, the coefficients that give the Ramanujan vector field to the pth power? What's some application of this?
Yeah, so some applications are, I still didn't do the computations, but Hossein has some conjectures in the end of his paper about this about this thing here, about this e to the p minus e. Okay, so now that we know how to compute directly the e to the p, we can attack these conjectures that relate to his conjectures that are related to the Grothendieck-Katz conjecture. So Hossein maybe can talk a little bit about that more.
The Ramanujan vector field, the solutions are transcendental.
Yeah.
In particular, the corresponding Grothendieck-Katz conjecture, in this case, the hypothesis is not satisfied. But whatever p curvature is, the p curvature is not zero. So he can verify with this equation explicitly that the p curvature is not zero because he has explicit form. But
Yeah.
the first statement I said is a consequence of the Grothendieck-Katz conjecture. It's a very tiny consequence, but anyway, it's a consequence. If you take a differential equation,
The microphone maybe?
And the whole story started from this EP minus E, this statement that he has written here, is in the kernel of phi. At the end, it shows that the E2, E4, E6 are P integral.
Exactly.
And we want to do these things in the case of Calabi-Yau context, which the statements are not trivial. So the idea that we are training ourselves in the case of elliptic curves to go to a Calabi-Yau context.
Exactly. And another thing that maybe we can do is try to eliminate this this restriction on 2 and 3. So there is a way of there is like how can I say this? A similar setting, a very similar setting, in the case where we just invert the 2, okay, over z 1 over 2. And we can try to do the same thing in this case and see what we get, okay? Mm-hmm. This is another possible way to go.
And the last question, so is there any reason we should be considering, for instance, greater powers of the Ramanujan vector field? For instance, if you take e to the p, then again to the p, this is also a derivation, right?
That's a good question. I don't know.
Okay.
Can I?
Yeah, of course.
So,
so maybe I have a question. Maybe this question goes also to Hossein.
Uh-huh.
But what happens in the case? I don't know if you know the case of the Calabi-Yau modular forms and the modular vector field in the case n equals to 3.
Yeah.
So can we use the same procedure? And then the dimension is 7 or maybe 8.
Yeah.
So then maybe we use just 3 vector fields that we have exactly the somehow some
The SL2 structure and everything, right? Yeah, you know what for me it looks is that we are using a very strongly the results of Swinnerton-Dyer regarding the modulo P relations between Eisenstein series. So I think that first we have to find some modulo P relations between Calabi-Yau modular forms, and to try to do the same thing, you know, because this Q expansion morphism, computing the kernel, you have to use the congruences between EP minus 1 and 1, and EP plus 1 and E2.
Yeah.
So I don't know. For me, I don't know if Hossein has some idea, but for me, it's clear that we have to prove congruences between the series first to arrive at a similar setting, at a similar, to use the same method.
Yeah.
Yeah.
So the modulo P in this three-dimensional space, there is some curve which can be formulated in something called Hasse-Witt invariant, so on in this alpha P. So idea is that to try to use these more algebraic geometric things to generalize the thing. Otherwise, the Q expansion and this to see what is exactly the Swinnerton-Dyer things in a Calabi-Yau variety, it will not work. But anyway, it is under construction.
Yeah. We also have other. For other congruent subgroups of SL2Z, we have other, because in the case of the Ramanujan, it is constructing, the solutions are giving the full modular forms.
Yeah, exactly.
But we have other congruent subgroups that maybe we have some analogous of Ramanujan vector field there, and maybe, I don't know, if try the procedure there, and then, Hossein told, in the case of the Darboux-Halphen.
Yeah, exactly.
Well, I think anyway, the idea is that if we at least the Darboux-Halphen case also, it would be good to learn things. Because in the Darboux-Halphen case, we don't have also Swinnerton-Dyer stuff, all these congruences. So maybe one can learn. And maybe I ask the online audience if there is no. Okay, if there is no question, so thanks again, Frederico. 11:50. We have